Okay, we're going to start with a little example which is very similar to the warm-up from last time. Which of these events is most likely to happen when flipping a fair coin? Flip 2 or more heads when flipping 3 coins, flip 20 or more heads when flipping 30 coins, and flip 200 or more heads when flipping 300 coins. In order to find these probabilities, we could use the theoretical probability. These are all binomial probabilities, so we could calculate them. And at first glance, you may think, oh, those are all 2 out of 3, so it's a 2/3 probability. They're all equally likely, but that is not the case. So you have to consider that with a fair coin, you would expect about half of the coins to be heads, the other half tails. So when you have 3 coins, it's pretty likely that you're going to flip 2 or more heads. But when you have 30 coins, you're going to expect it to be much closer to 15. And when you have 300 coins, you're going to expect it to be close to 150. So the larger the amount of coins, the more unlikely it gets. So we are going to look at a little simulation for that. And on StatCrunch, we have the ability to do a coin flipping simulation. So this allows us to do a very similar experiment without actually having to toss the coins. And we can look at how many times we get at least 2 heads. So over here I can do 1 run and it's going to give me 3 coins. Over here we have 1 head, 2 tails, and so here's the number of heads. And then I can do this again and again, or I could do 5 runs at a time, and so on. Just to speed up the process, I'm going to look at 1,000 runs. And so it says the probability, which is equal to the proportion, is 0.517. So if I do more runs, let's say, close to 10,000, it's going to get more and more accurate over here, get closer and closer to that theoretical probability. But you should have the idea that it's going to be something close to 0.5. Okay, so now we're going to look at the second example where we had 30 coins, and we're looking at the probability of getting at least 20 heads. And we can do, 1 at a time again, and you can see we have 17 heads, and that's going to put it right here at 17. So to speed up the process, again, I'm clicking at 1,000. So it looks like the probability is close to 0.045, and I can do this more and more times, and the probability is going to get closer and closer to that true probability, which we can calculate with a binomial distribution. This looks like it's pretty unusual. Before we had close to 0.5, now it's close to 0.05. So meaning it's unusual to get at least 20 heads out of 30. And then we can look at the third scenario where we have 300 coins, and I'm sure you can guess it's going to get even more unlikely. So we're going to look at 1,000 runs here, and we don't have any that have at least 200. So let's maybe do 10,000 again. And even out of 10,000 tries, not a single one actually had 200 heads. So this is extremely unlikely. And so you can see those 3 probabilities are different. Okay, so I wanted to look at the idea of a sampling distribution. So with a sampling distribution over here, we're going to look at rolling a die 5 times. We're going to calculate the mean value of those rolls. We're going to calculate the variance, which is the standard deviation squared, and the proportion of odd numbers of the results. And what do we know about that behavior over here? So in our first sample, we had a sample mean of 3.4. In the second sample, a sample mean of 4.4. And over here on the right, we have that sampling distribution of all the different samples of 5 rolls, and calculated all the means. So all outcomes are equally likely, so the population mean is 3.5. We could calculate that because each outcome from 1 through 6, each has the probability of 1/6, and then we can calculate the sum of x times p of x, or we could actually put 1 through 6 into list 1, put 1/6 into list 2, and then do the 1-bar stats. So that's going to give us a sample mean of 3.5. So here's the histogram of that sampling distribution, or of 10,000 trials. and you can see it's centered at 3.5. And keep in mind that we started with a uniform distribution because each outcome is equally likely. So even though we started with a uniform distribution, the distribution of sample means is going to be normally distributed. This second slide looks at the variances. So you can see this is the sampling distribution for the variances. So each time we calculate the variance, and then we plot it on a graph over here. And the mean of those, all outcomes are equally likely, so the population variance is 2.9. Again, something you can calculate with the 1-bar stats. The mean of those trials is 2.88, which means that it targets that population variance. So variance is an unbiased estimator, just like the mean is. You can see that this graph is skewed to the right. So variances tend to be skewed to the right. The last one we're looking at here is the proportion. So we're rolling the die 5 times again, and we're looking at the number of odd numbers. So in our first example, it was 0.2, second one 0.4, 0.8, and we're going to graph that over here. It's centered right at 0.5, which is what we would expect. We would expect half of the numbers to be odd and the other half to be even. And so again, our proportions also is an unbiased estimator because the mean of our sampling distribution targets that population mean. And we can actually look at simulations for that as well. Okay, so this is what we talked about last time, looking at the central limit theorem. When we're looking at really starting with any distribution, as long as we have a sample size large enough, the mean of the sample means is going to be equal to the population mean. So that's right here. The standard deviation of the sample mean is going to be equal to the population standard deviation divided by the square root of n. This is often called the standard error of the mean, and this is going to be very important when we look at confidence intervals and hypothesis test. So when we start with a normal distribution, we have over here sample size 1. We can see that the distribution of sample means is going to be normally distributed. When we take a sample of 10 and calculate the mean, and we're just taking repeated samples of 10, we can see that we have a shape that looks more and more normal. And with a sample size of 50, it's going to be a normal distribution over here, and you can see that it is much more narrow than the one above. So that has to do with our standard deviation divided by the population standard deviation divided by the square root of n. So that kind of squishes the whole distribution together. So that's when we start with a normal distribution. If we start with a uniform distribution, remember the uniform distribution is symmetric, so it's going to take not a too large of a sample size in order to look like a normal distribution. So here's a distribution for a sample size of 10, and down below for a sample size of 50. And the next one is a U-shaped distribution. Again, it's symmetric, so it's not going to take a very large sample size to start looking normal over here. So one more thing I wanted to look at in StatCrunch. So over here, looking at our sampling distribution, we can actually simulate the same thing. We'll get very similar pictures to the previous one. And so if I start, let's look at a right-skewed distribution. With a right-skewed distribution, I can pick again, do I want to pick 1 sample, 5 samples, or 10,000 samples? I'm going to start with a small sample size, pick just 1 sample of 2 values, and then calculating the mean. And then doing that over and over again. So I'm going to do 10,000 or 1,000 over here. And you can see that the distribution is starting to fill in, but it's still skewed to the right. So I can go up to 10,000. It will make it fill in a little more, kind of those holes in between, but you can see it's a right skewed distribution. When I increase my sample size to 5, and let's say again I take 10,000 samples over here, close to that, you're going to see that it's starting to look more and more normal. It's still a little bit skewed to the right, And then if I go to a larger sample size, like our requirement was, or our rule of thumb is at least 30, you can see it's going to be nice and normally distributed, or approximately normally distributed. And you can see each time I increase my sample size, the distribution gets smaller together. One last thing I can do, I can actually make my own distribution, and so I can make it, maybe we have a bimodal distribution over here. This is approximately symmetric, so it may not take a terribly large sample size in order to make it normal. So let's try a sample size of 20 over here. And you can already see it's nice and normally distributed. You can also compare the standard deviation of the original distribution and the standard deviation of my sample means down here. And you can see that the standard deviation is going to be divided by the square root of that sample size. So just as we had said on that slide.